This is a follow-up of a proof of concept I made 2 months ago. I used an Arduino-based digital-to-analog converter together with an op-amp to create a signal that could control the output of an eBay buck converter. This time I will make a simpler circuit that will just accept a PWM signal to control the converter. That makes it much more user-friendly than the previous version. I will also show you each step on the way so you can create this circuit yourself if you want. Almost all the eBay converters use a controller IC like the one in the picture above. And all these ICs have something in common, a feedback pin. This is why I chose to create a generic solution around this pin. Just grab a converter from eBay, apply this technique, and you're good to go. The controller IC is outputting a constant PWM signal to control the MOSFET that switches the input power so current can flow to the output side. Inside the controller IC is a stable voltage source, probably a Zener diode, that outputs a fixed voltage. Its value can be anything, but usually very low, like 1 or 2 volts. At the same time, the IC is constantly comparing the output voltage to the fixed voltage and makes a decision. Is the output higher than the internal reference voltage? Decrease the PWM duty cycle. And if the output voltage is lower, increase the duty cycle. This all happens fast, so the output voltage remains quite stable. The result of this is that the voltage at the feedback pin is the same as the reference voltage, even though they are not connected. It's all done by the actions of the IC. All of this would only give us an output voltage equal to whatever the reference voltage is. Fortunately, we are allowed to feed the feedback pin anything we like. The common thing to do when designing a generic DC converter is use a potentiometer so we can feed it a fraction of the output voltage, leading to a higher output voltage we can control ourselves. And then do the same for current. And then multiplex both signals into a single one. Replacing the potentiometers on the converters with a digital variant seemed to me like the obvious solution, giving me instant control of the device. These digital potentiometers, however, are very limited in the voltage they can handle, so not a very generic solution for me. Great Scott on YouTube did a video on that approach. To control the device, we need to influence the feedback pin. The voltage on the pin will always be the same because of the controller IC's hard work. But we can change how hard it must work to keep it at that level. If we add current to the pin, for example, the controller needs to remove current to keep the voltage at the same level. It does that by lowering the PWM signal, leading to less voltage on the resistor network. The first thing we need to do is set up the converter to output whatever we want at maximum. For me, this is 5 volts, because otherwise the lamp would be too bright for me. But I can imagine it to be 13 volts, for charging a car battery, for example. Please note that always on is not a good practice in general, but this is a device that does that by design already, and we are simply adding the option to dial it down. But to be fair, we could turn this upside down without too much trouble. The always on method, however, allows us to set a very precise upper limit, even when the add-on circuit fails, so I'll go for that. To control the device, I must solder a wire to the feedback pin, and one to the ground of the IC, because otherwise the signal will be meaningless. Because the device is full on by default, we only need to add current to the feedback pin to control it. An off by default device would be controlled by removing current. Now I am going to use one side of a potentiometer, so I can connect 5 volts to a variable resistor to dump current into the feedback pin. I want to know what resistor to use to completely turn off the device. It turned out to be 3.95 kilo ohm. For extra science points, I will calculate the needed current for this, so we can potentially control it from any other voltage as well. I is V divided by R. I is 5 divided by 3950, is 0.0012 amps, or 1.2 milliamp. Luckily for me, I did the measurement with the same voltage as I will use to control it automatically, so I only need to know the resistor value. Well, this is the circuit. From left to right, the PWM signal first goes through a 5K resistor to limit the current stress on whatever we use to create the signal. Then we have an inductor-capacitor pair to smooth the square wave out. Next, we want to amplify the signal but not drain the capacitor too much. So, a resistor with a transistor follows. And because I threw in a random NPN transistor with unknown gain, I choose to limit the current by a resistor slightly lower than the value we obtained in our test. This resistor later turned out to be not low enough. But I fixed that. Finally, the signal is sent to the feedback pin, and the ground is shared with both the circuit and the sender of the PWM signal. Normally, when amplifying a PWM signal, we would implement a push-pull configuration to send the signal to the feedback pin. But since we are only interested in adding current, we would throw away a lot of the resolution because it could also remove current, and add a risk of driving the target voltage or current above the desired limit we just set. Building the circuit went quite well. The components are close together, but that did not create any problem. I used some clay to keep all the components stuck to the board, while soldering the bottom side. When that is done, I removed the clay and started working on bridging connections, wire and such. Look at it. It's working. While testing off camera, I discovered that I was 0.1 volt away from being able to turn the converter off completely. To fix this, I would have to be able to provide a small bit of extra current. I decided not to replace the resistor, but solder one in parallel to the bottom of the circuit board. This is the working prototype, without all the probes, meters and wires. It is 3 cm long and 1 cm wide, and costs less than $1 or euro to make on materials.